So apparently I am the very last speaker in this event, and I'd like to thank the organizers, I'd like to thank the attendees for being so patient and for waiting for the mechanical panel. So my topic of presentation is rotating equipment engineering. So with the presentation, I'll try to bring you closer to the oil and gas and petrochemical industry, because rotating equipment engineering is one of the major branches of mechanical engineering, which is actually quite active in oil and gas and petrochemical industry. So we'll talk what the rotating equipment are. I'll also talk about the tasks of the rotating equipment engineer during the project phase and also during the maintenance and operation phase. And I'll briefly talk about the employment opportunities in the Azerbaijani market. So let's go ahead. What are rotating equipment? So the rotating equipment are the equipment which impart or extract energy from the fluid by moving the fluid. It could be a pump, it could be a compressor, it could be a steam turbine or gas turbine. And when we talk about the rotating equipment, then we have to actually consider four important components. These are the driver, driven machine, auxiliary equipment, and the coupling. So normally we have, in this example here, we have the electric motor as a driver, driven machine is a pump, then we have the transmission unit between the two, which is a coupling, and then we have the auxiliary equipment, which is actually, in this case, used for sealing purposes, for shaft sealing purposes. And whenever we want to troubleshoot, maintain, install, or commission a rotating equipment, we have to consider, we have to take all these four components into account. Okay? So these are the typical examples for the driven machines. The driven machines are the machines which actually impart energy into the fluid. So the pumps, compressors, blowers, decanters are the good examples for the driven machines. And then we have the drivers, which are used to drive the driven machines. And these machines are typically steam turbine, gas turbine, or diesel engine. They are meant actually to extract energy from the fluid, yeah? And of course, we have the transmission units between the driver and the driven machine. The speed increasing gearbox or speed decreasing gearbox is a good example. Then we have the clutch, which is meant to engage or disengage the driver from the driven machine. And then we have the typical couplings, yeah? And of course, as I have already mentioned, we do also have an auxiliary equipment. Auxiliary equipment are quite important for the smooth operation of a rotating machine. So this might be a lube oil unit, as you can see in this picture here. The lube oil unit is used for the lubrication purposes. It could also be used for the control oil purposes. So this is actually quite a big unit. For example, here in this case, it's for the compressor unit, which is driven by a steam turbine. It has centrifugal pumps, lube oil pumps. It has coolers. It has a lot of valves, pressure control valves, a lot of gauges, actually lube oil tank, heaters, and so on. And we do also have like the cooling unit. For example, if we want to cool the lube oil, then we have to need some auxiliary equipment. So this is another example. So what are the tasks actually? What are the tasks of the rotating equipment engineer during the project phase and during the maintenance and operation phase? So actually, the typical project cycle in the oil and gas and petrochemical industry looks like that. It starts with a feasibility study. It's a study whether the project is really worth to study, to start with actually. So, and then it goes ahead with front-end engineering design, and then we start the execution phase. We do the detailed engineering, we do the procurement, construction, commissioning, like pre-commissioning, commissioning, and then the plant is ready for operation. We do the performance test, production test, and then the operation and maintenance phase starts. And during the whole project, and during the operation and maintenance phase, the rotating equipment engineer is very closely involved. And how is he involved? So these are the tasks of the rotating equipment engineer during the project phase, which I have listed here. Actually, everything starts with the design, as you may know. So the rotating equipment engineer is responsible for, first of all, designing basic rotating machinery requirements, like making basic design requirements for the rotating machines on the plant. Let's say we want to build a refinery or we want to build a urea plant. So we have to, first of all, develop some general requirements. So the kind of requirements are being developed for some other equipment as well. So for the static equipment, for the instrumentation, for the electrical equipment. But the rotating equipment engineer is mainly dealing with the development of the design specifications for the rotating machinery. And once the general design specifications are defined, then we can go ahead with a detailed engineering design where we have to specify the exact parameters of the rotating machinery which we are going to utilize in our plant. It could be a centrifugal compressor, it could be a steam turbine or a gas turbine. And this is quite a long procedure. This is quite a time-consuming procedure. And these design documents are being developed in order to make bid requisitions in the next stage. Because once we have designed everything, once we have actually determined the design requirements, and not only the design requirements, but also some other requirements regarding work of supply of work or supply of scope, then we can actually make requisition bids to the vendor. So we have to purchase this rotating equipment. So the requisition bids are being made to the vendors, and the vendor makes like bid proposals. Like they propose rotating machinery in return, and then the rotating equipment engineer must do actually technical bid evaluation. So he has to investigate all these documents. He has to see whether the rotating equipment being offered is in conformance with the standards that are mentioned in the design specifications, whether the vendor can fully provide all the scope of work and scope of supply. So, and of course, once the vendor has been selected, once the rotating equipment has been selected, then the rotating equipment engineer during the project phase can also make some workshop visits, can go to the vendor workshop and witness the performance tests and some other inspection tests. Okay, so this is an excerpt from the basic design document for the rotating machinery. Here we have it's a table of content. So let's go ahead with detailed engineering. Here we have this requisition for the centrifugal compressors. It's a table of contents, and as you can see here, we have the scope of supply, scope of work, capital spare parts. So we have to mention all these kind of things before we can make a requisition to the vendor, yeah, as a rotating equipment engineer. And this is a typical data sheet for the centrifugal compressor. We have actually some standard data sheets according standards. We have some standards like API standard, standards for the rotating machinery being utilized in an oil and gas industry. So, and they have their standard requisition data sheets. So this is a typical requisition data sheet for the centrifugal compressor. And before, the rotating equipment engineer must fill out this document, at least partially, and send it to the vendor. And then this document must be filled out completely before we make a purchase order. Okay. So once we are done with the design, once we have purchased the equipment, we have procured everything what we need to install on our plant. The next stage is, of course, construction. We start installing the rotating machinery on the field. And once we have installed, then the next phases are pre-commissioning and commissioning. So during the pre-commissioning and commissioning, we have some activities like alignment, erection of auxiliary equipment, some piping work, some oil flushing, some steam flushing, some turbine driver solar run, and the mechanical run tests. Okay. So this is a typical alignment procedure that we are doing. Once we have installed the rotating machinery, the driver and the driven unit, we have to make sure that the driver and the driven unit are well aligned. So for the simple turbine, it can be a one day long procedure. But for a big machine, like a big centrifugal compressor driven by a steam turbine, it could take even it could take months actually to make proper alignment, because we also have some other factors like piping and so on to be taken into account. And once we have done the alignment, we could also start doing the lube oil flushing. Actually, lube oil flushing is one of the most important activities during the commissioning stage. Let's say we have a big rotating equipment, and this big rotating equipment is being supported by the lubrication system, as I have already mentioned, which is quite a big system comprised of a lot of piping, a lube oil tank, coolers, and so on. And when we install the unit is not well cleaned actually. So we have to make sure that the lube oil which we supply into the bearings, into the control system, into the gearboxes is very clean. So that's why we have to, first of all, clean the system, and we are using the original lube oil for the cleaning purposes. We are building a recirculation arrangement, and we are recirculating the lube oil. It could take it could take even months actually in order to have proper results in the end, in order to properly clean the whole lubrication cycle. And we could also use some like thermal shock effects, like increasing and decreasing temperature or air bubbling effect, in order to actually facilitate the lube oil flushing and in order to speed up the lube oil flushing procedure. And in the lube oil flushing, during the lube oil flushing, we are putting some meshes onto the return line into the lube oil tank, as you can see. And the top meshes were removed after the second flushing, whereas the bottom meshes were removed after the 15th flushing. So, and we actually, like this, we did 15 flushing recirculations, and it took like 2 weeks. And as you can see, the top meshes are quite dirty, but the bottom ones are very clean. And of course, we have some acceptance criteria regarding the size of the particles and regarding the number of the particles on the meshes before we can proceed, actually. So, and then we do the mechanical run test. It's another commissioning procedure. So once we have aligned, once we have lube oil flushed and everything is okay, we have to check whether the equipment runs smoothly without any vibration and temperature rise. So we are actually running the equipment like for 2 to 4 hours, depending on the size of the equipment, and we are taking records, actually, vibration records, temperature records, noise records, in order to ensure that the rotating equipment is well aligned, the rotating equipment runs smoothly. So these are not actually run under operating conditions, under actual operating conditions, because we haven't started up the plant yet. We might not have the proper operating pressure and temperature available to do the performance test, actually. So that's why it's just a basic mechanical run test in order to see that we have some, the equipment runs smoothly. Okay? So once we are done with the commissioning, what is the next stage? The next stage is the plant is ready for the operation and maintenance. And we have, during the maintenance and operation stage, the rotating equipment engineer is basically responsible for the reliable operation of the rotating machinery. So we want to have rotating machines running as long as possible without any interruptions. So in order to provide for that, we have to have proper preventive, predictive maintenance techniques. We have to do proper troubleshooting, yeah. And we have to actually have some well-educated technicians, well-educated site engineers on site, so that they don't make any mistake, resulting in a big trouble for the whole plant, yeah? So if we look at the lifespan of rotating equipment, we can see that if it's typically it's 30 years, the lifespan of a rotating equipment, and only the first 3 years actually is about design, manufacturing, and commissioning, and performance tests. The remaining 27 years, or 90% of the life cycle of a rotating machinery, is about operation and maintenance. But it's quite important that during these 3 years where we have design and commissioning, you don't make any kind of design mistake. You install the equipment properly, because a mistake in this phase can cause long run troubles for the end user, because the end user would suffer from it continuously in the future if you have a mistake, if you have made any mistake here in this stage. Yeah. Okay. So typically the objectives of the end user is actually maximizing the reliability, maximizing the product throughput, and minimizing the operating costs. So let's take SOCAR ammonia urea complex as an example. At SOCAR ammonia urea complex, we have quite a lot of centrifugal pumps, and these centrifugal pumps are just like main centrifugal pumps without any standby. Yeah? And if let's say a process air compressor trips there, then the whole plant will have to stop. So the urea production will stop. And so like considering that the total daily production is 200 tons per day, and considering that the price for the urea is $170 per ton, and if we stop the plant for 3 days, the revenue loss for the plant would be like $1 million. So, and this kind of a trip in a centrifugal compressor might be due to unskilled maintenance of the compressor or its auxiliaries, or it could be also, of course, it could be due to the unskilled or due to some troubles in the turbine, like because the compressor itself is driven by a steam turbine. So any kind of a small mistake could result in a big revenue loss for the whole plant. And actually, it's not only about the revenue loss, it's also about the image loss, because the client is waiting for the product. Yeah. So actually, the other important task of a rotating equipment engineer is troubleshooting. So troubleshooting is very critical. So, and in order to troubleshoot, you have some techniques. One of the most widespread techniques is our CFA analysis, root cause failure analysis, where you first define the problem, you collect data, you identify possible causal factors, and by eliminating the possible causal factors, you end up with a root cause. And then once you have found the root cause, you can start generating a solution, and then you can implement the solution. Yeah? So typically the causes, the causal factors of machinery failures are the process condition changes, installation errors, operation procedures, design shortcomings, or component wear out. So I want to show you an example, a case actually, where I have, from my experience, here we have actually a steam turbine. Like it's a steam turbine of a natural gas compressor. And normally a steam turbine has an integrated governor valve. Actually, governor valve is meant to adjust the flow rate into the steam turbine depending on the load on the steam turbine. So, and the governor valve has an actuator and has a lever. And the actuator is meant to lift the valves, to control the valves here, as you can see. These are the valves. And the higher the lever is lifted by an actuator, the more the valves are lifted, and the more steam goes into the steam turbine. Okay. So here we have the typical, like, expected valve lift curve from the manuals, from the data sheet of this specific steam turbine. And here the steam flow rate is plotted against the valve lift. Yeah. As you can see, we did a turbine solo run test in order to see whether, because before we can do the MRT, mechanical run test, connect the coupling and do the mechanical run test, we have to do turbine solo run test. We have to ensure that the turbine is in a good condition. So we did a turbine solo run test, and during the test we have noticed that the valve lift was like 4 millimeters, whereas the measured flow rate was 1.5 to 1.80 tons per hour. And when we look at this diagram, we can see that the valve lift at 4 millimeters should actually generate around 4 tons per hour of flow rate. Yeah? Something was wrong, so we couldn't get enough flow rate actually. So we wouldn't be able to get the design flow rate here. because the valve lift was already 4 millimeters, and at 4 millimeters valve lift, we were getting the flow rate which we had to get at 2 millimeters valve lift, yeah? So that was an issue. So in order to solve the issue, we did a root cause failure analysis. So as I have already mentioned, the first stage in the root failure cause analysis is actually defining the problem. We defined the problem, we collected the data from the trends, from the DCS and so on, and we listed the causal factors. What could be a root cause? What could be a possible root cause? For example, one root cause could be actually a choked flow passed by foreign material. So it could be some foreign material could be there in the somewhere between the valve and the valve seat, and it could cause the less flow rate than we expected. So in order to investigate this causal factor, we actually opened the turbine triple throttle valve and the governor valves, and made an overhaul inspection and the boroscope inspection, and we found out that there is no any foreign material there. So everything was okay. So meaning that this causal factor is actually not likely to be the root cause of this problem. And after eliminating some other causal factors, we came to the conclusion that the insufficient valve size was an issue. The valve was not chosen properly in the very beginning during the design stage. So this is a design shortcoming actually. So comparing to the steam turbines in the other plants, similar steam turbines with the same power, the valve size was actually much less than it had to be. So we had the valve size was 22 millimeters, whereas the valve size in the other steam turbines in other plants was like 28 millimeters. So this was identified as a root cause and actually as a possible, a very likely cause. And the solution was provided. The solution is actually, of course, because it's not, it's very costly to change the valve itself. We decided to increase the valve size and the valve seat size. So the vendor came to the site, they did some modification works, and they increased the valve size and the valve seat size. And then we did the turbine solo run again. And according to the results of the turbine solo run in the later stage, we could achieve the results that we wanted to achieve. So at 2 millimeter valve lift, we were already achieving 1.5 ton per hour flow rate of a steam, yeah? Okay, so I will also briefly talk about the employment opportunities in Azerbaijan. So actually, you can mainly be employed in oil and gas and petrochemical industry. Here I have listed some companies where you can work. So these are, for example, SOCAR. SOCAR has a lot of subsidiaries where you could work. SOCAR ammonia urea complex is a good example. At SOCAR Polymer and BP, you can work in operation and maintenance phase, basically. And then we have some companies like SOCAR KBR, SOCAR Foster-Wheeler, Wood Group, Wood Group, where you can actually be in the design stage. Like they are actually basically, they are making some front-end engineering design for the projects which are being implemented by BP and SOCAR. So you could work for those companies as well. Okay, that's all for me for today. Do you have any questions? Thanks.